Good afternoon. So today we will go over a short section, which is the last one from this chapter. We will talk about the relative maximum or minimum of a function of two variables. So in the big scheme of things of this class, we don't really emphasize this topic too much. It's also a matter of interest in the interest of time, because there are other more important topics that typically you don't want to squeeze them too tight over the end of the semester. So I decided on this section to just go over the concept of a relative maximum minimum and not the absolute maximum. Also for a function of two variables, just because it's important to know there are some differences from the equivalent topic from Calculus 1. So in Calculus 1, remember, as a brief over review from earlier times, right, from Calculus 1, one immediate application of the first derivative is to, for instance, figure out when a function has a local minimum or a local maximum, as opposed to an absolute minimum or absolute maximum, right? So the absolute maximum is kind of self-explanatory, right? So if there is such a value that is the largest of all values, then that's an absolute maximum, and same thing, the analogous thing for the lowest possible value of the function, if there is one. The relative is a local property, right? So the local max-min means that the function should have a maximum or a minimum in some neighborhood around that point in question, and depending on if the function is differentiable at these points, then these points, the relative minimum or maximum, are among the so-called critical points of the function, which, remember, are the points where the derivative is either is equal to 0 or doesn't exist, right? So in this particular class, I'll go over the concept of a relative or the local maximum minimum for a function of two variables and the equivalent of the second derivative test from Calculus 1. Remember, the second derivative test in Calculus 1 stated that if at a critical point the second derivative was strictly less than 0, the point was a relative maximum or a local maximum, and if the second derivative was at that point was greater than 0, that was a local minimum. And if it was equal to 0, then the test is inconclusive. So we have something like that or equivalent to this for a function of two variables. And I'm not going to go over the proof of the second derivative test. I'll just state it. And I want to just emphasize that you will see some type of points. Something is wrong actually with this pen. Let's see. I see some so derivative. Some of the virtual ink didn't show up here. So there is also a type of point that is not going to be seen in two dimensions, right, for a function of a single variable. For example, a saddle point, which is typical for a function of several variables, or two variables in this case. All right, so with this preliminary stuff, let's go over again, as always, with an intuitive definition first. So suppose we have a function of two variables, f of x, y, and we say that the point AB is a local maximum for the function f of x, y, if, as you may guess, f of x, y is going to be less than or equal to f of AB in some neighborhood of the point AB in the domain AB, in the domain of the function. So just the region around the point itself, right? If this is the point AB, if you can find an open region around the point for which this inequality holds true, then that's going to be a local maximum. And of course, analogously, is going to be a local minimum if f of x, y is greater than or equal to f of AB, again in some neighborhood of the point AB. As always, think about some visual analogy of what happens here. If the function itself represents an altitude on a hill, So xy is the longitude, latitude, right? It's the geographical position. And then the value of the function is the altitude on a hill. Then obviously the local max is going to correspond to peaks, local peaks, and local minimum is going to correspond to bottom of valleys. More or less. Maybe valley is not the correct analogy, but you know, the bottom, I forgot actually the word, the geographical word that I'm trying to have in mind. You know, like the bottom of a pail, essentially. So, all right. So how do we actually figure out the these points? Well, again, just like in Calculus 1, as it turns out, if f of xy has a local maximum or minimum on the point AB, then as it turns out, then the partial derivatives at that point, partial x at AB for f, partial y at AB for f, vanish at that point. So these points are among the so-called critical points, except that critical points now are the points where these derivatives are equal to 0, or the derivative doesn't exist. But again, we're going to focus on primarily on the cases in which these partial derivatives exist, at least in today's presentation. So the second derivative test for any of these points, right, for which the partial derivatives vanish, right? So suppose f of xy has so the theorem actually needs to say more than just vanishing at partial derivatives. It says that if the function has second order derivatives or second partial derivatives, right? These need to exist for the theorem to work. Well, after all, it's called the second derivative test. And the first partials vanish at the point. So, and partial x of f at AB is equal to partial y at AB equal to 0. Then the test itself basically states something in three cases. So there are essentially three possible results that the test will give you. First of all, we're going to need a quantity. So there are three cases. We're going to need a quantity called the discriminant, which is this denoted by D, which is partial x twice, partial y twice, minus partial xy to the power 2. This is basically the discriminant of a derivative of the Jacobian matrix, actually, as it's called. So denoting this combination by D, then we have basically three cases at each point AB, right? So all of this evaluated at the point AB. The first case is if the discriminant at AB is greater than 0 and partial x twice at AB is greater than 0, then the point itself is a local maximum. Local minimum. Second criteria, if again the discriminant is greater than 0, partial x at AB less than 0, then the point itself, AB, is a local maximum. By the way, make sure to watch the second part when I'm going to show you with Maple some of these examples to see how they look like. And then there is a third case, which is specific to a function of two variables, basically. So if you have the discriminant, this D at AB less than 0, strictly less than 0, then AB is a so-called, is neither local or, so it's neither maximum or minimum, but it still has some specific shape in the form of what we call the saddle. Meaning that if you basically go on a path on a hill, to use the same analogy, toward this point, it's going to be either toward the maximum or toward the minimum, depending on the path you choose across the surface that represents the function z equals f of xy, and then through that point. Again, it'll be much more clearer with an example with maple. And the saddle name is pretty suggestive. It does look like a saddle around that point. So let's see actually how this translates in practice, this test. Oh, and by the way, importantly, as always, if these conditions are not the same, I mean, they don't hold, then the second derivative test is not going to be conclusive. So for example, if d equals 0, then test is inconclusive. The point itself could be max, min, or neither, depending on the case. It's just that the second derivative test, as stated here, will not apply. And we'll introduce, we'll show you an example with that as well. So let's go over a couple of examples. Let's start as always with something that is easy to differentiate, just to see how this works. Finding the critical points often is tedious, and obviously, just to illustrate the concept, we choose example that we can do this by hand. If not, you're going to have to obviously use approximations or a computer algebra system. So let's take the function x squared minus 12xy plus 8y third, and let's start by finding the critical points. We're going to need partial x, obviously, first. Let's actually start here from the left side. So partial x is 3x squared minus 12y, and that's it. Partial y is minus 12x plus 24y squared. We're going to need later the second order partial derivative, so let's write them down here on the top. Partial x twice is 6x. Partial y twice is 48y. And finally, partial xy, the mixed second derivative, is going to be minus 12. It's a constant. So if we set this equal to 0 and solve this as a system to find all critical points, now realize that there's not going to be an algorithm to solve it. Typically, these are nonlinear equations, so you have to do your best with the algebra to see how you can come up with the roots. Most of the time, you want to factor everything you can, right? So for example, on the first equation, I can pull out 3x, and you're left with x minus, no, not 3x, sorry. Let's just divide by 3 to make the numbers easy. I can divide by 3, so I get x squared minus y equals 0. In the other one, I can divide by 12, and I get minus x plus 2y squared equal to 0. So the best you could do, of course, is to make a substitution. I can replace y with x squared in the first equation, substitute in the second equation, and I get minus x plus 2 y squared, which is now x squared, quantity squared. So keep in mind this substitution, and let's work our way out with this with the second equation. Let's see, y equals x squared minus, oh, I made a mistake here. I gotta, yeah, let me fix it actually on the, I'm gonna do it on the next page. I just forgot one factor here. So let's start over with the critical points. So divide by 3, I forgot that 4. So x squared minus 4 times y equals 0. And divide by 12, that makes it minus x plus 2y squared. That's fine. Let's see what's the easiest thing. I think the easiest thing is just to replace now x with 2y squared from the second equation, right? And then substitute in the first one. So I get 2y squared to the power 2 minus 4y equals 0. That makes it 4y fourth minus 4y equals 0. And then this factors into, I mean, if you cancel by 4 here. That factors into y times y third minus 1 equals 0. So there will be actually two critical points, because from this equality you get either y equals 0, and from the substitution over here the corresponding value of x is 0. And again, the other parenthesis here, y third minus 1 could be 0, which means y could be 1. And again, going back to the substitution, x is 2 times 1 squared, which is 2. So again, it's important to write them in the correct order as a point xy, with the x coordinate first, obviously. We have basically two critical points, 0, 0, and the point 2, 1. All right, so let's do it on let's continue on the second page with the second derivative test. All right, so I copy the function one more time. All right, the function one more time here on the top, and then partial derivatives of the second order that we're going to need for the second derivative test, and the critical points are 0, 0, and 2, 1. So first of all, the discriminant in our case is partial x twice, which is 6x times 48y minus negative 12 squared, right? Partial xy to the power 2. If we simplify this, this is 288xy minus 144. So now you simply apply the criteria for each critical point, right? So starting with the discriminant, again, look back on your notes on those three cases. So if I plug in 0, 0 into the discriminant, that's 288 times 0 minus 144. That's strictly negative, which means 0, 0 is a saddle. So you are automatically in the third case. And again, I'll run the example with Maple to show you how it looks like. Then what about the other point 2, 1? What is this discriminant 2, 1? So we're going to replace x with 2, y with 1. So you have 6 times 2 times 48 times 1. All right, minus negative 12 squared. That makes it, let's see, 288 minus times 2 minus 144. That's 400. Anyway, it's positive. That's the important thing. It's 432, which is strictly positive. So now you're either in case 1 or 2. To decide which one is which, you're going to have to compute the second partial derivative with respect to x at the same point. So you're looking at fxx. There's no y there to plug in, so it's just 6 times 2. That's 12. That makes it greater than 0. From these two and the second derivative test, we conclude that 2, 1 is a local minimum point. Okay, so here's an example in which the test is inconclusive, and again, I'll show you this with Maple as well. Let's say the function is, so that's the second example. Let's say the function is given by x squared y e to the minus x squared minus y squared. And take a moment to compute the partials yourself, just as an exercise, right? So partial x should be, we have the product rule, the chain rule, so 2xy e to the minus x squared minus y squared plus x squared y, and now we differentiate the exponential with respect to x. Let's do partial y now. Again, the product rule, x squared times 1 times the exponential. Continue with the product rule. Now we differentiate the exponential with respect to y, and we get this. Believe it or not, actually, we can actually do this by hand, these critical points. You just have to basically pull out as much as you can from both partials. So partial x, you can pull out 2xy, the exponential, and then you're left with 1 minus 1 minus x squared y. Excuse me, 1 second. So if I pull out so 2xy, so you're left with just x squared, yeah. 1 minus x squared. This is set equal to 0. And then partial y, you can pull out x squared and the exponential. And then you're left with 1 minus 2y squared. See, when you look at the critical points, you got to make sure to take all possible values. It's not just the parentheses equal to 0. So when you solve this as a system, you know, how many ways you can, how many solutions can you find? So notice that if x is 0, look at the factors outside the parentheses. If x is 0 and really y can be anything, this is a critical point, right? Because all derivatives are actually equal to 0 if x is equal to 0. If y is 0 by itself, that cannot be, because y is 0 makes partial x 0, but then partial y can never be 0. Unless x is 0, but that's already taken into account here. So the point 0, 0 is already taken into account when you realize that x0 and y arbitrary is a critical point. Then there are other old-fashioned critical points coming from the parenthesis itself. There's actually 4 of them, because independently, the first parenthesis is 0 if x is plus minus 1. And the second parenthesis is 0 if y is plus minus 1 over square root of 2. So basically we have 4 critical points, right? Because you have all possible combinations, plus, plus, minus, minus, plus, minus, and so on. And this guy 0, y. So I'm going to leave you as an exercise to evaluate the nature of these points yourself. I don't want to do partial derivatives. I guess, let me think a little bit. Yeah, so I'm going to do it probably with Maple because it's less tedious. I don't want to do, let me think a little bit. Well, let's see what happens. Partial x. I'm pondering the idea if I have to do if I should do the second derivatives. I guess we should do it because it's easy to see that the discriminant is 0. That's what I'm trying to show you. And therefore, the criteria doesn't apply. Right? It also doesn't apply because the partials are, the second derivative is should be 0 at some of these points. So let's see with the second derivatives what happens with them. So partial x twice. Let me think a little bit. You know what? Let's actually do it with Maple, just because I think it's not worth it to do it on the notes. So check for the last part of this lesson. We're gonna do this with Maple, all of these second order partial derivatives, because it's too tedious. But the point is, and we'll finish the written part with this, the discriminant at these points, at the point 0, 1 is 0, so therefore the second derivative test does not apply. And you'll see that some of these points are minimum or maximum depending on the value of y, but we'll see that actually with the graph on Maple. So stay tuned for the demonstration on Maple, and with that, that's it for today.